Everybody, welcome back. We're continuing chapter 2 with a discussion on scientific notation. So scientists and engineers regularly encounter very, very small and very, very large numbers. We can measure time periods as short as 0.0000000000000000001 seconds, a fraction of a second, and we can measure distances as great as 14 billion light years. So we have this huge span of measurements that we have to cover in science, from the very, 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 very small to the very, 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 very big. And so to do this, we use scientific notation because these very, very small numbers and these very, very big numbers have a lot of zeros, right? Look at all these zeros. And so by using scientific notation, it's going to condense these numbers into a format that's easier to read and write, so that we can easily work with these very, very small and very, very large numbers that have a whole bunch of zeros without having to keep track of counting how many there are. We can display them in scientific notation much more compactly and make them easier to read. So scientific notation always has two parts. It has the decimal part, which we also call the coefficient, and it has the exponential part, which is base 10 raised to an exponent n. So you see here the two parts. We have the decimal part. That's the value that represents kind of the quantity, the amount of stuff. We also call that the coefficient. The decimal part's always going to be the number between 1 to less than 10. So you shouldn't have two digits to the left of the decimal point. You wouldn't write like 11.2 because that's greater than 10. You just want one digit to the left of the decimal point here for your coefficient part to be properly displayed in scientific notation. And then on the exponent side of things, we have base 10. And scientific notation always uses base 10. There's other types of notation that may use base 2 or other bases, but in scientific notation, the base is always 10. And then the exponent can be any number, and it can be positive or it can be negative. And that tells us essentially how many zeros we have. And then if the zeros are greater than 1 to display a large number, or if the zeros represent a small number less than 1. So if we have a positive exponent in our scientific notation, let's just write our general formula for scientific notation here. You have your coefficient a times 10 to the n. So this is your exponent. So if the exponent is positive, you have a positive exponent, it's 10 multiplied that number of times. So if our n is 1, or sorry, our n is 0, means it's 10 multiplied one time, just 10, or the number 1. If our exponent is 1, means it's 10 multiplied one times. If it's 2, it's 10 times 10, 10 multiplied 2 times. If it's 3, it's 10 multiplied by itself 3 times, 1, 2, 3, to give 1,000. So the higher the exponent, the larger the number for a positive exponent, going from tens to hundreds to thousands. If it was 10 to the 4th, that would be 10 times 10 times 10 times 10 equals 10,000. So with positive exponents, the larger the exponent, the bigger the number. Each time the exponent increases by one digit, you add another 0 to the number, 3 zeros, 4 zeros, 2 zeros. If you have a negative exponent, here's our exponent. If you have a negative exponent, like 10 to the negative 1, a negative exponent means that it's 1 divided by 10 times itself as many times as the exponent shows. So 10 to the negative 1 means it's 1 divided by 10 times 1, 10 times itself one time. 10 to the negative 2 means it's 1 divided by 10 times itself 2 times. 10 to the negative 3, that's 1 divided by 10 times itself 3 times. So each time the exponent increases, the digit gets larger with a negative sign in front of it, it means we're dealing with a smaller and a smaller number. 10 to the negative 1 is 0.1, 10 to the negative 2 is 0.01, 10 to the negative 3 is 0.001. So with negative exponents, the larger the n when it's negative, the smaller the number. And each time you increase the negative digit by 1, it gets higher, -1, -2, -3. You're adding a 0 to make the number itself smaller. So to kind of summarize, positive exponents mean large numbers that are greater than 1, right? We're dealing with big numbers in the tens, the hundreds, the thousands, the 10,000s, the 100,000s, the millions. And if we have a negative exponent, we're dealing with small numbers that are less than 1. 0.1, like decimal values, 0.1, 0.01, 0.001, 10 to the negative 4 would be 0.123, 0.0001. So each time the exponent increases with a negative sign in front of it, you're dealing with a smaller and a smaller increment. Okay, so let's talk about converting numbers into and out of scientific notation. So if you have a number that's greater than 1, a large number, what you're going to do is you're going to move the decimal point to the left until you just have one number remaining to the left of the decimal point, and the rest of the numbers are going to be to the right of the decimal point. So if we look down here, we have 5,983. This is where our decimal point would be. So we're going to move it over 1, 2, 3 spots so that we end up with just one number to the right of the decimal point, sorry, to the left, one number to the left. And we count how many spots we moved it. So we had to move it 3 spots to get it. So there's just one number to the left of the decimal point. And that means our exponent is 3. 3 spots equals exponent of 3. Move 3 spots left, so it's times 10, always base 10 to the third because we moved 3 spots left. So each spot you move to the left is adding 1 to the exponent. If we had an even larger number, let's say we have 1,507,123. We want to put this in the scientific notation. We'd find where the decimal point is. It'd be right here if there was one. And then we move it to the left until we only have 1 digit remaining to the left. So 1, 2, 3, 4, 5, 6. So I had to move it 6 spots left. So that means my n equals 6. So my number would be 1.507123 times 10 to the 6. So for numbers greater than 1, big numbers, grab the decimal point, move it to the left until you only have 1 digit remaining. Count how many spots you had to move it, and the number of spots you moved it to the left, that's the value of your exponent. And it's positive because we're dealing with a very large number. Okay, so for small numbers, numbers that are less than 1, that are decimal values, we're going to do the same thing, except for we're going to move the decimal to the right instead of to the left. So for small numbers, numbers less than 1, again, we're going to locate the decimal point. Here we have 0.00034. So here's our decimal point. And we're going to grab it and move it to the right this time, 1, 2, 3, 4 spots, until we only have one non-zero number to the left. So we end up with 3.4. And then we counted how many spots we moved it. We moved it 4 spots. So n equals 4. And it's negative because we moved it left. Sorry, moved it right. I'm getting my left and rights mixed up today. Terrible day for that. And so this is how you would convert this number into scientific notation. You always locate the decimal point, and then you move the decimal point to the left or to the right so that you only have 1 digit remaining to the left of the decimal point. You count the number of spots you moved it. That's the value of your exponent. And if you had to move it to the left, then you have a positive exponent. It means you were dealing with a large number. And if you had to move it to the right, meaning you were dealing with a decimal value, then you have a negative exponent. Okay, let's do another practice one. Let's take this one and convert it into scientific notation. So you grab the decimal point right here, and I have to move it 2 spots over. So my number ends up being 1.23, right? Ends up right there, times always base 10. And I moved it 2 spots, so my exponent is going to be 2. And I moved it to the right. So it's going to be -2. We'll do one more. Okay, so grab the decimal point. Let's count how many spots we need to move it. We're going to move it to the right. This is a decimal value, a value that's less than 1. So we're going to move it 1, 2, 3, 4, 5, 6, 7. 7 spots to the right. So we're going to get 7.58 times 10 to the -7th. We moved it 7 spots, and the negative sign means we moved it to the right to turn a decimal value into scientific notation. And you see all these zeros got dropped. We don't have to include them in the scientific notation, which takes this really long number and makes it much easier to write. We'll talk about when to drop the zeros for large numbers in scientific notation when we get into sig figs, but you'll be able to do it with large numbers too, depending on if there's a decimal point shown with the original number or not. Okay, so when you convert a number into scientific notation, you need to check the value and the number or the sign on the exponent part. So the value of the exponent part, what n is, tells you how many spaces you have to move, and the sign on the exponent tells you what direction, left or right. Okay, so let's do some practice. Let's convert these numbers in standard notation into scientific notation, and we'll convert these numbers that are in scientific notation back into standard notation. All right, so to convert into scientific notation, if there's no decimal point shown, then you put it where it would be. This is a large number, it's greater than 1, so we're going to move the decimal point to the left, 1, 2, 3, 4 spots. We end up getting 6.6599 times 10 to the 4 because we moved it 4 spots, and we moved it to the left, so that's why the 4 is positive. It's representing a large number that's greater than 1. So you can always do a little quick check if you're worried about if you got the positive or the negative correct on your exponent. If you're dealing with a big number that's greater than 1, your exponent should be positive. Let's do the next one, 0.000946. So you grab the decimal point and you move it to the right this time. 2, 3, 4. So we end up getting 9.46 for the coefficient part, 9.46 times always base 10. And we moved it 1, 2, 3, 4 spots. And we moved it to the right this time to take a decimal value and convert it into scientific notation. So we have a -4 for the exponent. Okay, let's take these ones here and convert them out of scientific notation. So here we have 7.4 times 10 to the 3. So I'm going to write my 7.4 here to get started, and then I'm going to look at my exponent. It's +3, so that means this is a large number that's greater than 1. So to get it out of scientific notation, I need to move the decimal point in the opposite direction that I moved it to get this into scientific notation. So normally we move the decimal point to the left to get a big number into scientific notation. So to get a large number that has a positive exponent out of scientific notation, we move it the reverse way to the right. So I'm going to grab my decimal point here. And I'm going to move it 3 spots backwards to the right to get it out of scientific notation. So here's 1, 2, 3. It goes here. And then I fill in those blanks with zeros. And the really cool thing about scientific notation, and what's going to be really handy about it as we get into sig figs, is that when something's written in scientific notation, only the sig figs are showing. So this number has 2 sig figs, 1, 2. So when we take it out of scientific notation, we write it with 2 sig figs, 7400 with no decimal point. If those zeros we had wanted to include as significant figures, we would have included them in the scientific notation. Because they're not in the scientific notation, it means when you take it out of scientific notation, you don't want to include those, so you leave off the decimal point, which these are not sig figs that way. And only your 7 and your 4 count as sig figs. And again, we'll get more into sig figs as we go through chapter 2, but that's kind of a sneak peek of what's coming up. Okay, let's do the next one. So we have 2.9 times 10 to the negative 4. So I'm going to start by writing 2.9, and I'm going to check my exponent. It's negative 4. So the exponent is negative. So this is a small number that's less than 1. It's a decimal value. So we need to move the decimal point to the left to get it out of scientific notation. We moved it to the right to get this original number in. So we need to move it to the left to get it out of scientific notation. We want to end up with the number that has some zeros in front of it that's less than 1. So I'm going to grab my decimal point here. I'm going to move it 4 spots to the left. So here's 1, 2, 3, 4. And then you fill in the blanks with zeros. And so we end up getting 0.00029. And you can always check if I converted this back into scientific notation and went 1, 2, 3, 4, I'd get 2.9 times 10 to the negative 4. So you'll get practice doing these on your homework. You should be able to go seamlessly back and forth between scientific notation and standard notation. Okay, so we're going to have to be adding and subtracting numbers that are in scientific notation. So when you add or subtract numbers that are in scientific notation, you need to do one of the following 2 things. You either have to write the number so that the exponent parts are equal. So they both have the same exponent, like here, they're both 10 to the 3rd. And then you can just add and subtract them. Or if the exponent parts are different, you can either take them out of scientific notation and add and subtract them, or you can shift the decimal point to make the exponents equal. And we'll do that on the next example. Let's start with one where the exponents are already equal. So we're going to add the coefficient parts, 2.5 times 10 to the 3rd plus 5.0 times 10 to the 3rd. So we're going to add the coefficient parts. So we get 7.5. Everything stays base 10. And it's going to stay times 10 to the 3rd because these were equal to begin with. So we don't have to change anything there. So we get 7.5 times 10 to the 3rd. And I like doing it this way. It's nice when the exponent parts are equal. Then you just go ahead and do your addition and subtraction like you normally would. Okay, what do we do if the exponents are not equal? In this case, we have 3.0 times 10 to the 12th minus 2.0 times 10 to the 1st. So we have 2 options. We can rewrite one of the numbers so that it has an exponent that's equal to the other one, and then add and subtract them like we just did. Or we can take them out of scientific notation, do the addition and subtraction, and then put them back into scientific notation. You can also use your calculator, which is, I think, what probably most of the class will be doing. But we want you to know how to do this by hand so that if you need to, particularly when you're taking in-class quizzes and exams, that you're able to do it by hand as well. Okay, so let's first write these so they're both have equal exponent parts and do it that way to begin with, and then we'll do it the other way. Okay, so we have 3.0 times 10 to the 2. I'm going to leave that one as is, and I'm going to change this one from 10 to the 1 to 10 to the 2. So if I want to change this to 10 to the 2, I want to add 1 to the exponent. That means I need to move the decimal place 1 more spot to the left. Move 1 spot left. So this turns into 0.20 times 10 to the 2. And now that we have identical exponents, we can do the math as usual. 3.0 minus 0.2 gives us 2.8 times 10 to the 2. So that's an example of changing the exponents. We could have changed the other one. Let's do that just to be thorough. Instead of changing 2.0 times 10 to the 1, changing this to a 2, we could change this one to a 1. So if we want to subtract 1, you move the decimal point to the right. So we'd get 30 times 10 to the 1 minus 2.0 times 10 to the 1. 30 minus 2 equals 28 times 10 to the 1. This isn't written properly in scientific notation. We have 2 digits to the left of our decimal point here. So we need to move this over and add 1. So we get 2.8 times 10 to the 2. And then the last way you could do it is just take the numbers out of scientific notation, do the addition or subtraction, and then put them back in. So 3.0 times 10 to the 2. We take that out of scientific notation. We have 3.0 times 10 to the 2. So we're going to move the decimal point 1, 2 spots over. So we have 300 minus 2.0 times 10 to the 1. We take that out of scientific notation. We're going to move the decimal point over 1. That's 20. 300 minus 20 is 280. And then if we wanted to report our answer in scientific notation, we take our decimal point 1, 2 spots. We get 2.8 times 10 to the 2. So you can use whichever one of these methods in your mind makes the most sense. They're both going to work equally well. You can write both the numbers so the exponent parts are equal, then do the addition and subtraction. Or you can take them out of scientific notation, do the addition and subtraction, and then put them back into scientific notation. Okay, so when you multiply numbers that are in scientific notation, I think it's a little bit easier actually than the addition and subtraction stuff. What you're going to do is you multiply the coefficient parts just like you would multiply regular numbers. You keep the base 10, and then you're going to add the exponents. So for example, on this first one, 5.0 times 10 to the second times 2.0 times 10 to the third. We're going to multiply the coefficients. So 5 times 2, that's 10, times always base 10. And then we add the exponents. Multiply, add. So 2 plus 3, 10 to the 5th. Now to write this in scientific notation, right? You notice this is a 2-digit number and we only want 1-digit numbers, 1 digit to the left of the decimal point for proper scientific notation. So we need to add a spot, move a decimal over, which means we need to add 1 to the exponent. So we get 1.0 times 10 to the 6th. And you can check this on your calculator, make sure you get the same thing. Okay, next one. We have 3.0 times 10 to the 4th times 4.0 times 10 to the negative 2. So we're going to multiply the coefficients just like regular. So we get 12 times always base 10. And then we want to add the exponents. 4 plus negative 2 equals 2. So 12 times 10 to the 2. And again, this isn't proper scientific notation. So we've got to convert it into proper scientific notation. We got to move the decimal point over there. So we have to add 1 to the coefficient. So we get 1.2 times 10 to the 3rd. So key things to remember when you're doing multiplication with scientific notation: multiply the coefficients just like in regular math, and then you add the exponents, and then adjust your number if necessary so that it's written final answer in proper scientific notation. Okay, so when you divide numbers in scientific notation, you're going to divide the coefficient parts just like in regular math. You keep the base 10, and then you subtract the exponents. So when you're dividing exponents, you keep the base 10 and you subtract the n, or the exponent part. So here we have 3.0 times 10 to the 6 divided by 2.0 times 10 to the 3rd. So we're going to divide the coefficients. 3 divided by 2 is 1.5. Keep the base 10, and then we subtract the exponents. 6 minus 3 equals 3. So we get 1.5 times 10 to the 3rd. 6 minus 3. Subtract the exponents. Okay, next one. We have 5.0 times 10 to the 4th divided by 2.0 times 10 to the negative 2. So again, we're going to divide the coefficients. 5 divided by 2 gives us 2.5. Keep base 10 times 10, and now we have to figure out our exponent. So it's going to be 4 minus negative 2 equals 2.5 times 10 to the 6th. And again, double check this on your calculators, but you should be able to do these ones without using your calculators. It's going to be actually faster as you get used to it to do these in your head and quickly write the answer than to be plugging things into your calculator. Okay, so that finishes our discussion on scientific notation. We'll be using that throughout the rest of the class. So take some time with the homework to familiarize yourself with it, get to know your calculators. And our next topic will be uncertainty in measurements and introducing the concept of significant figures. I'll see you then.